Hello, good morning, everybody. We are starting our second week of the São Paulo Advanced School in Quantum Fluids and Applications. And I thank you all for coming here, the ones that are from different places in the world and in Brazil, that you are presently here in the auditorium of the Instituto de Física de São Carlos. And I also want to thank you, all the participants that are following us on the YouTube platform from different parts of the world. All the talks are recorded and will stay as a collection of lectures for the advanced school. And you can later on even see again or think a little harder about the concepts that were introduced in those lectures. We're going to start the second week. Today we have a very interesting day with very important scientists. We're going to start with Professor Yukalov from Dubna, Russia. And then we're going to have William Phillips from NIST, from Maryland, the United States. And then we move it to Professor Daniel Kleppner from MIT, following by David Pritchard, also from MIT. And before David Pritchard, we have Thomas Kazanzer from Heidelberg in Germany. And then we end with David Pritchard. So it is a very good collection of talks. And we're going to start with the first talk that we'll be giving by Professor Vyacheslav Yukalov. Professor Yukalov has a very long curriculum. He was a student of Bogolyubov in Russia. So you see, he also got all the information directly from the main source. And he was a visiting professor in many, many places around the world, including many universities in England, Canada, United States, and also Brazil. He was a visiting faculty here during the year of 2009, 2010. And Professor Yukalov is one of the important theoreticians on the field of many-body physics, and he traveled in many, many topics. His research interest goes from both theory of Bose-Einstein condensation, from Gibbs-Urich mechanisms, inverse Gibbs-Urich mechanisms, from different methods to optimizing perturbation theory for dealing with those problems, correlated interaction theory, self-similar predictions, concept of stochastic instability, theory of clustering matter, theory of Bose condensation in many aspects. In fact, for many of the papers that Professor Yukalov is being done is very fundamental for many of the recent applications. For example, thermalization and non-equilibrium type of routes to equilibrium and routes to thermalization. He has a very nice paper on that a few years ago. I think there was more than like 8 years ago, giving very interesting concepts on the differentiation between a system that thermalizes or a system that's re-equilibrate. So Professor Yukalov has been working in many places, as I said, and his basis is the Dubna Theoretical Institute, the Bogolyubov Theoretical Institute in Dubna, which I had a pleasure to visit. And there they really touch many fundamentals of the many-body physics, including nuclear physics, as we all know. It's very famous in Dubna. And Professor Yukalov continue collaboration, and he's always open to nice discussions. And today, Professor Yukalov is going to tell us about spintronics with cold atoms in optical lattice. As you know, spintronics is one of the good applications for quantum fluids in general, especially in lattice. So, Slava, please, you can start your talk, and then at the end, I will return to place some questions from the audience and from the YouTube.
Okay, thank you very much, Vanderlei, for the introduction and for inviting me to give this talk. I also thank all the organizers for helping me in organizational matters, and I greet all participants. So I'm going to talk about spintronics with cold atoms and optical lattices, and here there are two co-authors, so I have to mention my co-author. This is approximate plan. First, I will say several words, what kind of atoms, how they are described, what is the general Hamiltonian, what magnetic fields are used, because having spins, it is interesting to have magnetic fields. And then I will touch the point that I'm considering insulating lattice. Then, in order to describe how the equations of motion are considered, it is necessary to mention what are methods of decoupling and of treating the system of equations. And at the end, I will mention how these points that I discussed can be used for creating different spintronic devices, mainly a memory device. So I'm considering cold atoms. We have angular momentum, and the field operator describing these atoms is a column with respect to the quantum number. And since I'm going to consider the lattice, and the lattice is assumed to have quite deep wells, it is reasonable to expand the field operator in Wannier functions. I keep in mind sufficiently low temperature, so it is possible to use single band approximation. The general system Hamiltonian consists of several parts. The single particle term for a while, where standard terms are included, as well as the external field of the lattice, or if there are other fields. Then the linear Zeeman term, and I will also take into account the quadratic Zeeman term, because as you will see, it can be used for a kind of governing the dynamics of spins. Then there is the term describing local atomic interactions and the term describing long-range dipole interactions. The linear Zeeman term has this form, quite known. Then the quadratic Zeeman term can in general contain two parts. One part is due to the static current quadratic Zeeman effect, and the other part is due to the alternating current parameter of quadratic Zeeman effect. The difference is that the static current does not need the application of alternating current fields, and this term is due to the application of usually radio frequency term from outside, which induces this special kind of term. And I will clarify what are the parameters of the corresponding interactions. So this is the static Zeeman quadratic term, which is due to the existence of the nuclear spin and corresponding hyperfine energy splitting. And the alternating current quadratic Zeeman term is proportional to this parameter that is defined by the Rabi frequency of the alternating field and the detuning transition from some internal transition. So local interactions are of usual form, having this form of expression, and this is the interaction which includes scattering length of the pair of atoms with angular momentum of the pair F, which is even here, and the projection operator onto the corresponding F state. So this is standard term. In addition, there is the term containing dipole interactions. In general, dipole interactions, they have not only this bare part, but they should be regularized in order to avoid some problems in the description, some short-term regularization, which takes into account that atoms cannot approach each other closer than some distance, and the long-range regularization caused by the screening, which arises when there are many atoms. And if they are in the trap size is smaller than this length corresponding to the correlations between atoms. But actually, these are not the main points. It's just for generality. What is important is this slide. Here are one of the main points. I do not consider the sample which is just placed inside an external magnetic field, but the situation is a bit more complicated. So suppose we have this sample. Of course, I am drawing this schematically. But this is a sample, and the sample is inserted into a magnetic coil. You see here the magnetic coil. There is an external magnetic field directed along the axis Z, and as far as this magnetic coil is a part of the electric circuit, which is schematically drawn here, there is the following effect. As soon as there is spin movement in the sample, the induced electric current in the coil, and as far as electric current in the coil induces magnetic field which acts back on the spins. So this is called the feedback field. It is created by the motion of spins inducing current, and current induces magnetic field. So this is important part of the setup which I'm going to consider. Not just magnetic field, but also the feedback magnetic field. In addition to the external field, it is possible to add some small addition which can be regulated. This part is a constant magnetic field, and this can be regulated, making it smaller or larger, and the feedback field. So this is the total magnetic field acting on the system. Feedback field is, as I already told, connected to the electric current arising in the magnetic coil. This process is described by the Kirchhoff equation, which can be rewritten in terms of the feedback field. So we have this feedback field, which comes from the Kirchhoff equation. What is here? It is the attenuation of the electric circuit, its natural frequency. And on the right-hand side, there is electromotive force that is caused by moving spins. Spins move, and they induce electromotive force that produces this feedback field. Then I return to the description of atoms. So expand on the field operator over Wannier functions that are supposed to be well localized, since I'm considering insulating lattice, and it's possible to make some standard simplifications in the Hamiltonian. It is possible to introduce local operators, local spin operator, and local density of atoms. It is useful to note that local spin operator defined in this way does not depend on either atoms are Bose atoms or Fermi atoms. This representation is valid for any kind of statistics, and it is easy to check that the left-hand side presenting the spin is really the spin operator satisfying all commutation relations of the spin operators. So we introduce these local operators and continue transforming the Hamiltonian, substituting there the expansion of the field operator over many functions and using these notations. What we have, the single particle term is this very simple expression, where this is effective energy that is given here. U here is the external field. Non-magnetic, magnetic fields are considered separately. Then we have local atomic interactions that are written here for the case of F1, just for concreteness. But it is not so important that it is F1, but what is important is that this local atomic interaction part, it is spherically symmetric with respect to rotations of spin. This is important. So in principle here, that could be the local atomic interaction term for other quantum numbers F. This is the main, but for concreteness, I write here for F1. This form is expressed through the effective interactions that are presented here, interactions of pairs of atoms. And now we go further to the most important terms of the total Hamiltonian. These are the Zeeman parts. This is a linear Zeeman term, which is exactly the same as usual. It's simple. And this is the part related to quadratic Zeeman terms. So these two parts, as I told you, related to the static current, a quadratic Zeeman effect, and the alternating current quadratic Zeeman effect. The total magnetic field, just for a reminder, I'm telling, contains the constant part of an external magnetic field, some additional part that can regulate the strength of the field, and feedback field. And finally, we have the dipolar Hamiltonian that also acquires this usual and known form. So we have the total Hamiltonian defined in terms of local variables like spins and density of atoms in wells. In order to consider the dynamics of spins, we need to write the evolution equations, Heisenberg evolution equations. And writing these equations, we notice that spin, of course, commutes with the single particle term, which doesn't contain spin at all. And also spin variables, they commute with the local field interactions, provided these are spherically symmetric, and they are assumed to be exactly such. Spherically symmetric with respect to spin rotation part commutes with the spin operator. So what is left from this Heisenberg equation is the commutation of the spin with parts of the Hamiltonian containing this spin. These are linear Zeeman term, quadratic Zeeman term, and the dipole term. So we now can write the equations of motion for this, for any component of the spin. Of course, as you know well, when you write microscopic equations of motion, you obtain the correlator of different orders between spin operators. What is possible to do is to use some kind of mean field approximation, but only for non-coinciding terms, because in general, in the equations of motion, we obtain this combination of spin operators. And we cannot decouple this combination using this mean field approximation because it is bad for any spin except large spins. And for example, for spin 1/2, this is not correct if we decouple this part in this mean field form. So we use the more general decoupling of this kind that is written here. And it is necessary to notice that this decoupling is exact for spin 1/2. Exactly, just because this part for spin 1/2 is 0, and here we have 0, and it is exact for large spin. But unfortunately, this is not the end of the story. As far as we are writing the equations of motion for spin operators in the system, for each atom, J here enumerates atoms in their well of the optical lattice. And there are many wells, and respectively, there are many atoms. So in the lattice, we can have 1,000 or several thousand of atoms. So we have several thousand of equations for spin components. How to describe this system of equations? In general, there are two ways. One simple way, we write the Heisenberg equations for the spin, and then turn each spin just into a classical vector, just considering that this is an average spin. This procedure gives us many equations for all these spins that compose the system. But what is possible to do is possible to put into computers these several thousand of equations and just consider their dynamics. This quasi-classical approximation has good sides and bad sides. Good sides is that, in principle, this description in the quasi-classical approximation is known to work well when there are coherent effects in the system. For example, if we are interested in the stage of the spin motion when there is coherent movement of spins, this is a good approximation. Also, it is good for very large spins, but it has bad sides as well. First, we cannot well describe the initial stage of spin motion because at the initial moment, the spin motion doesn't have yet well correlated spins and there is no coherent motion of spins. So this quasi-classical approximation just would kill all dynamics because the dynamics in the quantum stage starts with the spin movements. First spin movements of separate spins, then they start correlating and spin waves appear. And only after this stage, spin waves, they trigger the movement of spins in a more collective way. Then, if we use this kind of quasi-classical approximation, we just lose all this initial stage of spin motion and the presence of spin waves. And in order to push the spins that otherwise would stay forever in the initial position, it's necessary to push them. If we push sufficiently strongly, then we can organize some motion of spins and to describe the coherent motion. But all initial stage is lost, which is not good because the initial stage defines the delay time when spins start moving. Then there is another way to simplify a little the equations, and this can be done using scale separation approach. This approach is based on the fact that it's possible to notice that in the system of spins, there are several parts that move differently. there are parts which move fast and that move slowly. So to consider different variables which are of our interest, we can define the transverse spin variable as here, the variable that this defines how coherently spin move, so this coherence intensity, and the spin polarization along the axis Z. Then there are parts that are responsible for local spin interactions and parts producing spin waves. I do not write cumbersome equations here, just follow the main idea. So it is convenient to define dimensionless feedback field, which is divided by the quantity that can be called the attenuation related to the feedback field, because this parameter appears in the right-hand side of the Kirchhoff equation, and which describes the connection of electric circuit with the system. So this is the definition. Then we notice that we have in the system several parameters describing different kinds of attenuation. The attenuation of the electric circuit, the attenuation describing the interaction between the electric circuit and the system, then longitudinal and transverse relaxation rates of spins, and attenuation rate that is created by spin waves. If all these terms are small as compared to the Zeeman frequency, and the Zeeman frequency is defined by the external field. So if we take sufficiently strong external field such that there is this small parameter, then we can separate the variables in the equations of motion into fast and slow. The fast variables are the variables that have right-hand sides of the differential equations that do not disappear when we set small parameters to 0. Usually they are proportional to the Zeeman frequency, which implies that they are moving fast. So the transverse component and the feedback field, they are fast variables. And slow variables is the intensity of coherence and the spin polarization, because their right-hand sides are proportional to the attenuations, and in this classification, they disappear. Of course, they do not disappear when these parameters are kept, and we don't do this, but we know that these variables move much slower than these variables. The parts related to spin fluctuations also are fast variables. What we do later, so it's possible to solve the equations for the fast variables, keeping their slow variables as fixed, because as far as they move much slower, they can be considered as quasi-integrals of motion. So they are kept fixed, and then this allows us to solve the equations for fast variables. And then we substitute the found solutions of these equations for fast variables into the equations for slow variable, and average the right-hand side of the equations for slow variables over time and over small spin fluctuations. So this is the general procedure of scale separation approach, which allows us to obtain the equations for the coherence intensity and spin polarization that are sufficiently cumbersome, of course, but anyway, this is easier than consider several thousand of equations describing all atoms. In these equations, of course, they're cumbersome. It is very boring to look at them, and I tried not to write very cumbersome formulas, but I need to write down these equations in order to show what was actually solved later on. Here there is notation of alpha and beta. These are not just parameters, but these are functions which are called coupling functions because they appear when you describe the connection of the electric circuit with the spin system. So we have this complication. So there are functions of time also. It is possible to notice what combinations of parameters describe effective coupling parameter, coupling of electric circuit with spins, and spin fluctuation attenuation is of this order, which also possible to find from these equations. Then the quadratic Zeeman effect produces, it enters the equations of motion in this combination of the parameter that contains the part related to the static current Zeeman effect and alternating current Zeeman effects. The corresponding parameters described as this static and alternating current terms are here. And analyzing the equations of motion, it is possible to notice that the effective Zeeman frequency is not just that part that is related to the external constant magnetic field, but it contains as well this additional term that is due to the adjustable field and the part related to the quadratic Zeeman effect. So the quadratic Zeeman effect produces a kind of effective anisotropy, which changes the effective frequency of spin rotation. So what happens later? It is clear from the equations that it is possible to show mathematically, but it is also absolutely evident, I think, for everybody, that the strong connection between the electric circuit and the spin system appears only when there is a resonance between these systems. The resonance implies that the Zeeman frequency should be close to the effective rotation frequency of spins. If this is so, then there appears quite strong interaction between the electric circuit with its natural frequency that is assumed to be close to the Zeeman frequency and the resonance circuit. So the electric circuit becomes not just an addition that is not as important, producing only small fluctuation of spin, but it becomes quite efficient in the producing strong coupling between this electric circuit, which is in resonance with the motion of spins in the optical lattice. And as far as this strong interaction between a resonator made of electric circuit and the spin system appears only when there is a resonance, we need to satisfy this initial condition. So if there is no this initial condition, there is no resonance, and actually the electric circuit practically does not interact with spin system. But as soon as there is at the initial time this resonance condition, which can be adjusted because we can slightly change this adjustable magnetic field, and also what is important, we can change the parameter of the quadratic Zeeman effect. It is very quickly adjustable. And just in the experiment, it was demonstrated in several experiments. It can be varied. So varying these two parameters, we always can arrange this triggering condition, which corresponds to the resonance, and then there appears strong coupling between electric circuit and spins, and which influences strongly the motion. The following slide shows also a very important part. What kind of setup we are going to consider. It is not interesting just to take a system and to put some external field and consider small variations in the dynamics of spins. What we want to consider is a very strong non-equilibrium situation that we can organize in the following way. So suppose we have at initial time this spin system where there is optical lattice with spins that are polarized along the axis Z. Then we direct the external magnetic field in this direction of Z. And as far as spins are created by electrons, this situation corresponds to metastable state. This spin, they would like to reverse to the position directed down. Then, why do you need this kind of setup? Because of the following. Suppose we have these initial spins which are in metastable states. What doesn't make them possible to immediately reverse to their equilibrium situation? This is not possible because there is no resonance. And there is the quadratic Zeeman effect, which produces a kind of anisotropy. And to overpass this anisotropy, there is an energetic barrier. If this barrier is made sufficiently strong, then spin cannot go from this local metastable state and cannot overturn. It can be kept quite a long time in this position. But as soon we arrange this triggering condition, organizing a resonance, then immediately electric circuit starts interacting with the spins, and the triggering condition actually kills the barrier created by the quadratic Zeeman effect. And as soon as there appears a resonance, spin starts moving. It quickly overturns into the equilibrium direction. So we have the spin reversal, which happens during this time defined by these parameters that contain the attenuation of the electric circuit, the rate describing the strength of the interaction between electric circuit and the spin system, Zeeman frequency, and the initial spin polarization. Then, just to be more precise, it is possible to check what the values we need. For example, for these atoms, lithium, natrium, sodium, rubidium, which have F1. So here are the parameters of the typical spin systems. If we take the external field about 1 Tesla, then the frequency of the Zeeman term corresponds to 10 to the power 11. The interaction between electric circuit in the case of resonance and the spin system is proportional to this parameter, which becomes very sufficiently strong in the case of resonance. And we can estimate the parameters describing the static current quadratic Zeeman effect and alternating current quadratic Zeeman effects. They are emphasized here. So the term describing static current Zeeman effect can be made over the order of 1, but alternating current for typical parameters, alternating current Zeeman effect is rather small. So in this parameter, which contains the setup corresponding to the existence of the quadratic Zeeman effect, the main part is made by the static current. I'm saying for these parameters and for these particular atoms. Of course, there are other situations where the alternating current also can become small, but just for concreteness, I consider this case. So the parameter which corresponds to effective anisotropy that is created by the quadratic Zeeman effect can be made large, sufficiently strong, so if we remember the expression for the effective Zeeman frequency of rotating atoms, it makes a sufficiently strong energetic barrier for keeping at the initial time in this system spin polarized. But when it is killed, then there is a reversal during this time. Then we put all this machinery into a computer and solve the equations for spin motion, presenting here the spin polarization. So at the initial moment of time, we have a spin polarized along the axis Z. As I explained already, this is the metastable state, but for a while, when we have the strong quadratic Zeeman effect and related parameters, they can keep here for a long time. But as soon as we organize change in the parameters, the triggering condition, which describes the initial resonance in the system, spin starts overturning. So here, the reverse of the spin for different parameters of the system. So it reverses in different ways, fastly or slower, more fast, more slowly, and in different with different initial times. This is another picture with also different parameters. And what I would like to stress again, that the main idea was to keep the spin in some metastable states for the time we need. And as soon as we need to overturn it, we can immediately organize the triggering transition and organize the reversal of the spin. Why this is necessary, or why this is useful, to have the ability of organizing the motion of spin according to our will. Because the reversal time, which is estimated here, can be made very small. It is of the order of 10 in the power 10 seconds. So the spin can be reversed very fast. It can be kept very long in a polarized state, in a metastable situation, and very quickly overturned. Why this is useful? Because when we are making some kind of memory device, we usually need to satisfy two conditions. First, if it is a memory device, then memory is kept there by organizing the specific direction of spins. And suppose we organize the memory directing spins up. But if as soon as we want to change what is written there, to change what is in the memory, or destroy what is written there, we need to erase spins or to overturn them. And this mechanism, exactly what I had described, it allows to govern the spin motion. It allows to keep the initial spin polarization as a sufficiently long time and to reverse it in a very short time, in the moment when we need it. In this sense, motion and the reversal of spins is completely regulated by us. So this is what I wanted to tell, that as a conclusion, atoms and trapped atoms including, that are in optical lattices, they can serve a very efficient mechanism for creating effective spin systems that not only are interesting by themselves, even in the situations closer to equilibrium, but we can organize strong non-equilibrium situations with strongly non-equilibrium motion and organize the situation that can be used in spintronic, for example, in the memory devices. Thank you very much for attention. So there are some minutes left for questions. Hello, Andrei, where are you?
Hi, Slava. Let's first see if we have questions from the audience here. People that are present, you have any question? Yeah, well, we have one question here, just a second.
Thank you for the nice lecture, Dr. Yukalov. My question is the following. As a physicist, I like symmetries. We all do. You start with your system in a lattice, optical lattice, that breaks the rotational invariance. Of course, there are still, if it's like a square lattice, there are still cubic symmetries and stuff like that. But then you have a magnetic field in the z direction, you have the feedback field in the x direction, you have dipolar interactions that are non-central. So my question is, are the results and the conclusions particular to the system, or could you expect to observe things like that in other systems that possess different symmetries?
In the Hamiltonian, there are different parts. There are parts which don't depend on spin, and there are parts which depend on the spin, and you enumerated them. These are Zeeman terms and dipolar interactions. So I'm not sure that I correctly understood your question. If I correctly understood, you are asking what would be the difference if we take different geometries over the lattices. Is it?
Yes, something along that line, yes.
Of course, this can influence the parameters enter the system. As you saw, I have here a quite rich set of parameters describing the state and describing the atoms. And of course, including the parameters that describe how long can we keep them metastable state, they are related with the geometry of the lattice. So what you're asking is related to the choice of the parameters. Particular lattices, particular atoms will slightly vary the parameters.
Okay, thank you for your answer.
Slava, we have one question from the YouTube asking if this is valid for any lattice geometry, but I think you have answered already to Lucas that it is possible to generalize that. But you want to make any extra comment?
To generalize, considering different atoms, do you mean?
Yeah.
Yes, of course. I mentioned that when I wrote the part containing the interactions, I considered particular set of atoms in order to choose the parameter. Because when we are solving the system equations by computer, we need to put their numbers. Because of this, I had to choose some particular case. But of course, the situation will be the same for any system containing atoms for which we can write the equations of motion for the spin. Because the main point here is the original setup. It's not just the system in an external magnetic field, but it is in an electric coil which produces an additional feedback field. And this additional feedback field, as well as the existence of the quadratic Zeeman effect, they make us possible to regulate spin motion. These are the most important parts. So other types of atoms will slightly change the parameters, but the main idea is valid for any system. So two main points. We can organize metastable states, keep it long, and we can very quickly reverse the spin system at any moment we wish. This is the main points of regulating the motion.
Okay, okay. Thank you very much. Any more questions here in the auditorium? Okay, so let's thank again Slava for the wonderful seminar on this spintronics. I think this is a topic that has everything to grow in this field. So thank you very much, Slava, and I hope to see you in three-dimensional eventually here in São Carlos. And my best
I will be
regard
happy,
to
yeah.
Elizabeth and everybody in Dubina.
Yeah, I will be happy. It's my dream to meet you and to embrace.
Okay, thank you very much.
Okay, bye.
Okay, now that we had this first talk of the day, we're going to have a test for Professor Phillips. He's already on the room of the Zoom, and we're going to do a few minutes of test to make sure. So if you guys here in the auditorium wants to use these 10 minutes to have a coffee and return, because we're going to start in probably 10 to 15 minutes, not to have a delay, in order to be able to obey all the people outside the auditorium that are waiting for the talks. Okay? So we're going to make the test now. Bill, are you there? Okay. Okay, I'm going to ask you guys to be taking your seats so we can start on time. Hello, Bill, can you hear me?
Yes, I can.
Okay, I'm going to take my mask because I'm far from everybody else.
Okay, now we're getting an echo.
Yeah, we're getting some echo. Okay, I guess most part of the people is in the auditorium. We would like to have Bill here. We all know in person. It's always very nice to discuss with him and take him for lunch and dinner and have fun. But unfortunately, we could not have that this time. So we have you guys participating, some of the faculties here, but most of them online like Bill. But we hope that in the coming future, we all be able to be together and having this human contact that we cannot substitute by any other means. And that will be done soon, we hope. Well, I have to introduce Bill. Maybe nobody knows Bill Phillips. Normally, I used to say Professor William Daniel Phillips, but I know that he's going to cross that thing, he's going to say Bill Phillips. So that's the way we refer to Bill. He's a wonderful person, more than anything else. And he's been in São Carlos many times. I cannot even count how many times he has been here. He's been always a very nice reference for us in atomic physics and in metrology. He's an atomic physicist that graduated from MIT, and immediately after, he took a position at NIST, which is the National Institute of Standard and Technology in the United States, and that somehow matches very well his personality. Bill is a guy of precision, and he spent part of his life doing measurements. His original goal, I mean, he did the measurement of a proton, and he would like to measure magnetic field with high precision. And he ended by being the most important actor on the laser cooling field. He found a way of producing a beam of slow atoms that let us all enjoy life, have jobs, and doing wonderful research. So Bill was the guy that together with a few others developed the Zeeman tuning technique for slowing an atomic beam. And that was the initial push for all the area of laser cooling. People demonstrate our ability to control atomic motion. And because of this, Bill has been always an important person in the field. He got the Nobel Prize, everybody knows that, but he got many other prizes. But more important than everything else, he's a guy that enjoys the science. He enjoyed to teach science. He enjoyed to participate on the development of science involving cold atoms and involving some other things. And I have a pleasure to be part of some committees with Bill. And without Bill, probably this field will be a little different. So he's a guy for you guys young to have as a reference. And by the way, he works very hard. Nobody gets what Bill got without working hard. So I'm not going to give more details about Bill. Everybody knows he's one of those guys that when he is in the auditorium is filled. Probably he's coming to São Carlos in the coming future, and we're going to have this chance to enjoy once more Bill Phillips here in our environment. But today, he's going to give a talk in our school. This is an advanced school. It's mostly graduate students and postdocs participating in different parts. We have about 50 people here, another quantity like this following by internet. And I'm seeing that, Bill, the next day of the presentation, the hits on the YouTube goes about a few hundred. So I'm very pleased that we are doing this, because the things stay there and people can see the lecture, even not being present in the school or outside. They can enjoy your lecture anytime they want. So thank you very much for agreeing to give us a lecture. Bill, he can speak about many, many topics, and he offered a few, but we thought that an atomic superfluid Bose-Einstein condensate in a ring is a very nice application of those quantum fluids. And so we chose that topic as a topic for presenting to you in the school, and I hope we will enjoy. So Bill, now you have the word and you can present your lecture, and then I return for the questions. Thank you very much.
Thank you, Vanderlei, for that that very kind introduction. When you said that that anytime I'm in the auditorium, I thought you were going to say anytime that I'm in the auditorium, you can expect questions, because of course, as you know, I often ask a lot of questions. So I encourage all of you to think about the questions you have as we go through this talk. And I always write them down in my notebook, but I'm looking forward to your questions at the end. Anyway, we're going to talk about an atomic superfluid Bose-Einstein condensate in a ring. And you'll learn about what all these pictures mean in a little while. Many people have contributed to this work. The most important here is Gretchen Campbell. Gretchen is what I like to call the ringleader, leading the rings group. She's also my group leader, my boss. If she were here, she would give a much more intelligent talk about this subject. She's the leader of what I like to call the Fellowship of the Ring. And I also want to mention that we have lots of theory collaborators in addition to the experimental collaborators that I mentioned before. We're all part of the Joint Quantum Institute, which is a joint institute formed by the University of Maryland and the National Institute of Standards and Technology, with the participation and support of the Laboratory for Physical Sciences. Our work has been supported for many years by a Physics Frontier Center from the National Science Foundation. And I also want to mention that for young people in the audience, that we have lots of opportunities for study and research at NIST. There are lots of fellowships and scholarships available to people. So if you're interested in working with us, we certainly want to talk with you. So, coming back to the subject of the talk, an atomic superfluid Bose-Einstein condensate in a ring, and I want to mention that this is going to be just a sampling of some of the results from our lab. There are many other experiments and many other laboratories working on these kinds of experiments, and I'm going to be telling you about a few of the things that we do and some of the ways that we are thinking about experiments with Bose-Einstein condensates in rings. So let's begin with thinking about what is a Bose condensate. Well, in very simple terms, and I know that many of you know this already, but just as a quick review for some who may not be as familiar or may not have studied it recently, a Bose condensate is a really, really cold gas of bosons that has first been laser cooled and then evaporatively cooled. So the laser cooling idea is illustrated here, or at least the way we originally thought laser cooling worked. The idea is, if we imagine this as representing a one-dimensional gas, these being the atoms, in one dimension in a gas, some of the atoms are moving one way and some of the atoms are moving the other way. And we come with laser beams from both directions. And the laser beams are tuned slightly below the resonant frequency of the atoms. What that means is that an atom moving to the right is going to see the laser beam that's coming from the right Doppler shifted to a higher frequency. Because the frequency was too low to begin with, it means that this laser beam is shifted closer to the resonant frequency. The atom preferentially absorbs from this laser beam and it slows down. For an atom going in the other direction, it sees this laser beam, the one coming from the left, as being Doppler shifted to a higher frequency, and it preferentially absorbs from it and slows down. Of course, it absorbs some from the laser beam that would speed it up, but the point is that it preferentially absorbs from the laser beam that would slow it down. You can now expand this to 3 dimensions so that you have laser beams coming in from top and bottom and from backwards and forwards. And this configuration of laser beams is often called optical molasses. It was given that name by Steve Chu, who was at Bell Labs at that time, a long time ago, 1985. The idea being that molasses is a very sticky, viscous fluid, and the atom's motion is so strongly damped by the laser beams that the atoms feel as if they are in a viscous fluid. Well, that's the first step, laser cooling. I'm leaving out a lot of details about things like magneto-optic traps and about subdoppler laser cooling, a process that works even better than what I've described here to get atoms to even lower temperatures. But the point is, using techniques like this, one can get a sample of atoms that typically has temperatures of perhaps some tens of microkelvin. Then we go to the next step. We trap the atoms in a magnetic trap or in a laser trap. And if you're interested in knowing more about that, please ask me, but I'm not going to tell you about the details of the magnetic traps or the laser traps, but just the key thing to remember is that we can trap the atoms in a trap that does not heat them, a trap that is in some sense benign. That is, it holds the atoms without heating them or without cooling them, except for this process of evaporation. Now, evaporation is something that you all know something about. If your coffee is too hot, then you blow on it. Now, what's happening when you blow on your coffee? You are allowing the most energetic water molecules to leave the surface of the coffee, because the most energetic ones are the ones that leave, because they have enough energy to get out of the surface of the coffee. It means what is left behind has a lower average energy. That is, its temperature is lower. This is how we cool off coffee. You've experienced this if you go to the beach and you come out of the water and it's windy, you feel cold because the most energetic water molecules on the surface of your skin are leaving, and what's left behind has a lower average energy and therefore a lower temperature. We do exactly the same thing with our atoms in a trap, a magnetic trap or a laser trap. We allow the most energetic of those atoms to escape, and as a result, the atoms that are left behind have a lower energy, and the density of the atoms will increase as well. Even though we're getting rid of atoms, we can make the density increase because as the atoms have a lower energy, they're compressed by the trap into a smaller and smaller space. And then what happens is that when we get them cold enough and dense enough, they undergo this wonderful phase transition called Bose-Einstein condensation. So at the beginning, the atom is relatively hot. And when I say relatively hot, I mean hundreds, maybe tens or even 100 microkelvin, so very, very cold, but still too hot to Bose condense. And if we think about the quantized energy levels in the trap, the atoms occupy various of these quantized energy levels. But when the gas is what we consider to be hot and dilute, any given energy level has an average occupation number less than 1. In other words, it's unlikely that any given energy level that you would choose at random, it's unlikely that that energy level is occupied. Only a few of the available energy levels are occupied. This is what we mean by a gas that is hot and dilute. Now, what happens as we make the gas colder? In other words, we allow the most energetic of these atoms, the one near the top of the trap, to escape. And that means that the ones that are left behind are colder and more dense. So they're going to go to lower levels of the trap. And eventually it gets cold enough and dense enough that the average occupation number of the lowest energy levels in the trap is approaching unity, that it's highly likely that you're going to get some atoms in the lowest energy level. And now as you cool the atoms more and more, and the atoms undergo collisions, then we get a kind of Bose simulation, the sort of thing that creates a laser. The idea that occupied levels will be more likely to get more occupation as collisions happen, and the atoms can go into various states. They like, because they're bosons, they like to go into the states that are already occupied. And then we end up with a macroscopic occupation. A large number, a large fraction of the atoms are in the lowest energy state. And that is what we call a Bose-Einstein condensate. And one of the things I want to emphasize is that this is a phase transition. It's something that happens suddenly. That is, when you get the atoms cold enough and dense enough, then you suddenly start to build up a large fraction of the atoms in this lowest energy state. This was first observed for an atomic gas in 1995, and it resulted in the Nobel Prize for these three heroes, Eric Cornell, Wolfgang Ketterle, and Carl Wyman. And the picture that we're looking at here is showing the two-dimensional velocity distribution, so the projection onto a two-dimensional plane of the velocity distribution of a gas of rubidium atoms as it is evaporatively cooled toward Bose-Einstein condensation. So after a good bit of evaporative cooling, the gas, which started off at a temperature of some tens of microkelvin, has been cooled down to 400 nanokelvin. And what we're looking at here is the velocity distribution in this case, Vx and Vz, where the height of this pseudo three-dimensional picture gives you the number of atoms that have that particular velocity. And you'll notice that the velocity distribution is broad and featureless. This is the same sort of thing you expect to happen with any kind of a hot dilute gas that would exhibit a Maxwell-Boltzmann distribution of velocities, that is a Gaussian distribution of velocities. Well, the velocity distribution may not be exactly Gaussian as we get to low enough temperatures, but it still has this general feature of being broad and smooth. However, when the temperature was evaporatively cooled down to 200 nanokelvin, this big peak appears in the middle of the velocity distribution, and this is the atoms that are occupying the lowest energy state available to this Bose-Einstein condensate in this case, it was a magnetic trap in the presence of the other atoms, which form an additional kind of pseudopotential because of the repulsion between the atoms. This is the lowest energy state that those atoms can have in that potential. And you can see that a large fraction of the atoms are in that lowest energy state. And as the evaporative cooling continues down to a temperature of about 50 nanokelvin, this broad pedestal, which indicates the atoms that have not yet gotten into the Bose condensate, and it also indicates what the temperature of the atoms is. That broad pedestal almost disappears, so that we end up with a gas with essentially all of the atoms. We often have more than 90% of the atoms in the ground state. So just sort of a summary of the nature of an atomic gas Bose condensate. We use laser cooling and evaporative cooling. we produce a sample that often has on the order of 1 million atoms, sometimes more, sometimes less. But the point is that all of these atoms are in the same quantum state. They're in the same internal state, and they're in the same state of center of mass motion. That's what we mean by a Bose condensate. And the physical size can often be at least somewhat macroscopic, on the order of 100 microns. Young people can see objects that are only 100 microns across. And of course, a very important feature is that it's a superfluid. And we're here to talk about quantum fluids, which are often superfluids when they are bosonic gases. Now, one of the features of superfluidity is that we can have motion, circulation of the atoms with no dissipation. This is the same sort of thing that happens in superconductivity when the electrons or the electron pairs in a superconductor can flow without dissipation, without resistance. We get the same sort of thing. We can have our atoms flow without dissipation in our Bose condensate. So here I want to contrast the situation where I have a Bose condensate in a trap, and it's not circulating. It's just smooth and featureless. Here's a picture, an actual photograph of what it looks like. Here's a sort of a cartoon of what this Bose condensate looks like. And one of the, since nothing is moving, the quantum mechanical phase of the wave function of these atoms is uniform. Remember, velocity in quantum mechanics has to do with the gradient of phase. If there's no velocity, if these atoms are essentially motionless, they're in an eigenstate of motion. There's no net flow of these atoms. The phase is going to be uniform. Now, let's say that we induce circulation, and we'll talk a little bit more about how we do that, how we induce circulation into a Bose condensate. Then the nature of the circulation is that we get vortex motion. Now, what do I mean by vortex motion? I mean that in the center, there's an axis around which the atoms are rotating, and the density of the condensate is 0, where that at the center of that axis, and the atoms circulate around there. And the atoms circulate around there with a velocity profile such that the further away you go from the center, the lower the velocity is. In fact, the velocity goes like 1 over the distance from the center. Why? Because the atoms have a specific angular momentum. At least if I've got a symmetric trap with the vortex centered at the center of this trap, the atoms have a specific angular momentum. And in order for every circulating path to have the same angular momentum, I have to have the velocity go like 1 over the distance, because the angular momentum is equal to the azimuthal velocity times the distance from the center. So that velocity has to go like 1 over the distance from the center in order to have conserved angular momentum. And if I release this cloud of atoms, it's not featureless. It has a hole in the middle, a core. Now, it has to have a hole in the middle because if it didn't, you would have atoms with an indeterminate phase, because because of this velocity, the phase winds up by 2 pi going around once. Well, if I were exactly at the center, I wouldn't know what the phase was. And the only way that we can resolve that problem of not knowing what the phase is to have the density of the atoms at the center be 0. So there are no atoms who are confused about what their phase should be. All other atoms have a phase that depends on where they are azimuthally, and the phase, as I said, winds up by 2 pi for the lowest energy, that is the 1 unit of angular momentum, 1 h bar of angular momentum for each atom in the lowest state. Okay, now, one of the things I want to emphasize is that this core can be quite small, less than a micron. even though the size of this object might be on the order of 100 microns. And it is so small because of the interactions between the particles. The small size of the core is due to these interactions. So is the superfluidity, the fact that the atoms can flow without any dissipation, without any friction. Now, I want to mention, although I'm not going to talk about it very much, you can ask me questions about it if you like. Sometimes people talk about coherence, the idea that there is a well-defined quantum phase. If it's not rotating, the phase is uniform throughout the sample. If it is rotating, the phase is still well-defined. It winds up by 2 pi as you go around the vortex core. This relates to what people often call the coherence of the Bose-Einstein condensate, this well-defined quantum phase, the fact that it's describable by a wave function. Often that is lumped together with superfluidity, the idea that there is flow without dissipation. And people sometimes treat them as if they are the same. And sometimes they are, or at least sometimes I should say that the appearance of coherence and the appearance of superfluidity happen together, but not always. So I just want to mention that as a warning. So now we've been talking about a Bose condensate, the sort of thing that we might have in a simple magnetic trap. But I want to introduce now the title of the talk, which is superfluid atoms in a ring, a Bose condensate in a ring. A ring is even better. Why is a ring better? Well, let's look again at what happens when we've got a Bose condensate in a simple trap. So here's a simple confining potential that'll produce a nice featureless Bose-Einstein condensate. If it's got angular momentum, then when I release it, it'll show this hole in the center. When it's trapped, it'll have a small vortex core, usually so small that I can't resolve it by these pictures. But in any case, something quite small, something that's on the order of typically less than 1 micron. Now, what about a ring? A ring is going to have a potential like this. If I take a cross section of the ring, let's say that if I would go along here, here's the ring, the potential is low here and here, and that's where the atoms are. And there aren't atoms held here in the center. So this place where you would have the vortex core of this very small, unresolvably small hole, resolvable if you're in the trap. Okay, it becomes resolvable when you release the atoms. Instead, we have the atoms outside of that. We have no atoms here in the center, because in the center we have this repulsive potential that keeps the atoms outside here in the place where the ring has a minimum of potential. Now, why is this a good thing? Let's imagine that we have the ordinary simply connected Bose condensate, and there's some sort of a vortex in it. Now, the vortex doesn't have to be at the center. It can be essentially anywhere in here, but it has its highest energy when it's at the center. Why does it have a high energy at the center? Because that's where all the atoms are. So if the atoms are moving around the vortex core, there's going to be more atoms moving around the vortex core when the vortex core is at the center, because that's where the density of atoms is higher. So that means the kinetic energy associated with the vortex core is higher there, so its energy is higher. That means the energy is lowest at the edge of the cloud, and that's where the atom that's where the vortex wants to be, because it naturally wants to go to the place where the energy is lowest. Now, that energy has to be dissipated, but that's not too hard to do. In a sample where you have some of the atoms not Bose condensed, that is not superfluid, you can lose energy to the non-condensed fraction, and this vortex can escape. So the vortex is not stable if you put it in this kind of a simply connected Bose condensate. On the other hand, if you make a ring and produce a persistent current in the ring, so the atoms are circulating, then the place where the center of rotation is a place where there are no atoms. That means that its energy is very low. Out here, the atoms have a very low velocity. In here, the atoms, if there were any, would have a high velocity and therefore a high energy. But out here, because the velocity goes like 1 over the radius, the atoms are moving relatively slowly. And so they don't have very much kinetic energy. And in fact, the vortex is relatively stable, because in order for you to lose this circulation, you have to take this vortex core and move it so it was centered out here. That's going to take a lot of energy. So that's not going to happen. So this situation of circulation in a ring is a stable situation. Now, people have thought about this for a long time and wanted to make rings, but it turned out it wasn't that easy. It was hard to make the rings uniform, so that the Bose condensate would puddle up in some places, so you would not have a uniform condensate circling around the ring. And this is what happened for a number of years as people tried to do this. In our laboratory, what we did was we borrowed a trick from the Ketterle's group's first experiments to make Bose condensates. What they did was they took a magnetic trap that had a magnetic field equal to 0 in the center, and that's bad for reasons that I can talk about if you want to ask me, because the atoms can flip their spins there and be expelled from the trap. So they focused a laser beam into the center of the trap that is blue detuned from resonance so that it expels the atoms. I wish I had time to explain all these details. Many of you know them very well, but please ask me about them if you want to know about them. Anyway, you focus this laser beam in and expel the atoms from the center. So the atoms in their experiment formed a kind of a ring around this repulsive laser core. They didn't do any experiments that used that fact, and they soon changed their magnetic field configuration so they didn't have to do this. But we used that idea to take a regular magnetic trap that did not have a 0. We focused a laser beam in the center and produced a potential that looks like this sort of Mexican hat potential. And by making this very small, making a very tight trap so that the density of the atoms was very high, we were able to finally make a ring trap where the atoms extended all around the ring. Now, lots of other people have done this since then, and I think this list that I have here is probably not a very complete one. I do want to call out the experiments that Jean Dalibard has done at the École Normale in Paris and the Collège de France. Because a lot of the things that he's done are very similar to the things that I'm going to be talking about here, and they're very nice experiments. Now, remember, I promised you that if we have a ring, that the persistent current in that ring, the circulation of atoms in that ring, is going to be robust. It's going to be more persistent. It's going to be more stable, and this plot shows that. This plot here shows the probability of circulation remaining in the condensate as a function of the time that I hold on to it. Now remember, this is seconds, so this is a long time. So this particular curve shows what happens when we have a simply connected Bose condensate. So it's not a ring, it's just an ordinary blob of Bose condensate. We start the atoms circulating, and this shows the decay of probability. The lifetime is on the order of a half of a second. On the other hand, when we get the atoms circulating in a ring, and a ring simply means that we've put in this laser to repel atoms from the center, then the lifetime is very long. There's hardly any decay for the first 10 seconds or so, and then the atoms decay. And the reason they finally decay is that the laser beam and the magnetic trap are on two separate platforms, and they drift relative to each other. And this makes the trap itself unstable because the laser beam is no longer at the center of the magnetic trap, and then eventually the atoms are lost. So this proves just what I said, that if we put the atoms in the ring, that the atoms' circulation will be stable. Now, I was intending to tell you about a beautiful and elegant way of spinning up the atoms, but the fact is that even though it's beautiful and elegant, it doesn't work as well as some less elegant means of doing it. So I'm not going to tell you about it. Ask me questions if you're interested. Let's just go on to more experiments with the rings. So remember, I told you that this idea of using a laser beam to produce a repulsive barrier in the center of a magnetic trap had a problem because of the fact that the lasers and the laser beam and the magnetic components would drift relative to each other by a few microns, but still that was enough to mess things up. So in order to get around that problem, we decided to make an all optical trap. So we were just using laser beams to make this ring. So we had a ring-shaped laser beam. I can talk about how we make that if you're interested, but let's just for the moment ignore the beautiful techniques that go into making these ring-shaped laser beams. We focus that ring-shaped laser beam into the area where we want to trap the atoms, and we intersect with that ring-shaped laser beam a laser beam being focused with a cylindrical lens, so that we get a thin sheet of light, and the atoms are attracted to the places where the laser beam has its highest intensity, because we've tuned the laser beams below the resonant frequency, so the atoms are attracted, and we can make a very nice uniform beam. So here is a picture of atoms being held in this all optical trap that has been very carefully adjusted, and the students who did this are real heroes for working so hard to make this ring very uniform, and as a result they produce these beautiful ring-shaped condensates, and the currents in these rings can last for as long as 60 seconds on average. It's essentially limited by the fact that the vacuum in the apparatus is not perfect. There's these, in essence, these persistent currents last forever. They last as long as the atoms last. So now I want to introduce the idea that we can think of this ring of atoms as being a kind of circuit for the flow of atoms, in an analogy to atoms that are in, not atoms, electrons or electron pairs that are in a superconductor. If I have a ring of superconductor, I can induce a persistent current in that ring, and that current will last essentially forever. In the case of superconductors, a supercurrent can last for months. In our case, forever is about a minute, because we don't have a perfect vacuum, and the atoms in the imperfect vacuum will strike our very cold atoms and knock them out of the ring. But 60 seconds is an incredibly long time. And so, in analogy to superconducting electron pairs in a superconductor, we have a flow of atoms that can flow around this ring essentially forever. But as a circuit, this is a very boring circuit. A loop of wire is not a very interesting circuit, even though it can have something really remarkable, a persistent current. This is not a very interesting circuit, even though it can have something remarkable, a persistent flow of atoms that lasts essentially forever. We want to do something more interesting. We want to put a circuit element into this superfluid ring. And the circuit element that we're going to put in is again inspired by the superconducting circuits. What we're going to do is to put in a Josephson junction, a weak link. And the nature of that weak link is going to be a laser beam. tuned now on the blue side of resonance and the high frequency side of the resonance so that it repels the atoms. We're going to shine in a laser beam, and it's going to repel the atoms from a particular place on the ring. This is very much like taking a superconductor and installing in the ring an insulator, or for that matter, a region in space where the superconductor has been thinned out. Now, the classic Josephson junction is a very thin barrier of insulator through which the electrons can tunnel. But a Josephson junction doesn't need to be that. Here's a micro photograph of a Josephson junction that's made simply by thinning out the superconductor. Any kind of disturbance in the superconductor can make a weak link or a kind of Josephson junction, although it's not an ideal Josephson junction of the sort that represents a tunnel barrier. Now, in case you're wondering whether we should really call such a thing a Josephson junction, I asked Josephson if he was okay with it, and he said he was. So I think that I'm okay to call this a Josephson junction. And there have been a number of other people. Here's an incomplete list of some of the people who have been studying Josephson junctions in Bose-Einstein condensates. But typically, these people have not been studying them in a circuit. That is, they start with a condensate and they'll put a barrier between two parts of the condensate, very much the way Josephson originally imagined it, and study the behavior of these Josephson junctions. We're doing something a little bit different. We're putting the Josephson junction into a circuit. So here's our atoms in a circuit. You can't see it, but let's say that these atoms are circulating. And what I'm going to do is I'm going to put in the Josephson junction right here and turn up the power of the laser until the laser power is big enough that it breaks the flow. So the way in which the experiment is going to work is we're going to form a Bose condensate by evaporative cooling. We're going to just hold the atoms in the ring for a little while, let things settle down, let all the excitations that might have happened during the cooling process go away. And then I'm going to turn on the barrier beam. I'm going to always put it right here, but I'm going to turn it on to different heights. So sometimes it'll be higher, sometimes it'll be lower. Here's a picture where it's quite low. Here's a picture where it's very high. Going to leave it on for a while so that, again, any excitations that might have been caused by turning on the laser beam can go away. Then I'm going to turn it off. Then I'm going to turn the trap off and see whether we have circulation. And if we do have circulation, that expanded trap is going to have a hole in the center. I haven't described the details of why that is in detail, so ask me about it if you're interested. But if the circulation is gone, then we're going to get a featureless cloud with no hole in the center. So it's going to be easy to tell. So here's that same sequence of pictures. If the laser beam is very intense, then it's going to break the circuit. And what we're going to ask is, how intense does the laser beam have to be to break the circuit? Now, I want to introduce an analog way of thinking about what's going on in this superconductor. Imagine that I've got a stream of water going along at a certain velocity. And the depth of that water is proportional to how many atoms we have in our ring. And it produces what we call the chemical potential, or the mean field energy. The higher the density of the atoms and the higher the interaction strength between the atoms, essentially the higher this the water in the stream is. That is the analog that I invite you to think about. The total energy is equal to the kinetic energy plus this energy of interaction between the atoms plus the energy of the potential in which the atoms have. This is just a way of imagining what Schrodinger's equation would look like. There'd be an interaction term, there'd be a potential energy term, and a kinetic energy term. And so the atoms are flowing along here. But now let's imagine that I'm going to throw some rocks into the stream. That's going to raise the potential energy. So that term that was the potential energy in there, that's getting higher. As a result, the atoms have to go through a constricted channel. So since the flow is the same everywhere, because of course the flow has to serve atoms, so the flow has to be the same everywhere, the atoms have to be going faster here. Now, if I keep constricting the flow, the atoms are going to go faster and faster as they go past the constriction. And eventually, the velocity is going to get close to the velocity of sound. Now, I haven't talked very much about superfluidity, but the nature of superfluidity is that the atoms will flow without dissipation as long as the atoms cannot create excitations of their own and lose energy that way by creating excitations. Now, what are those excitations? They're phonons or vortices. And when the velocity of the atoms is high enough, it can create phonons, it can create vortices. And the simplest thing that happens is that when the velocity is equal to the velocity of sound, if there's some kind of a point-like perturbation, then the atoms can create phonons and they can lose energy to the phonons, and then they lose their superfluidity. So we expect the superfluidity to be lost when the velocity is on the order of the speed of sound. So we're going to do this experiment and measure what the critical velocity is. So here's the kind of experiment that we do. We start up the flow of atoms in the ring. We let them sit in the ring with a certain size barrier, which I've indicated here. We let them sit for 5 seconds, and then we see whether there is circulation. If there's circulation, the cloud looks like this. If there's no circulation, the cloud looks like this. In this plot, we varied the number of atoms, which varies the interaction strength between the atoms. And what I'm plotting here is the survival probability versus the interaction strength between the atoms. And what you see is that as you increase the interaction between the atoms, then the survival is more likely. And this is just what you expect, because it's the interaction between the atoms that creates the superfluidity. And the larger the interaction, the larger the speed of sound. So that means that the atom flow is going to survive longer. And that's exactly what you see here, that as the interaction strength is increased, in our case, by increasing the density of the atoms, the survival probability goes up. And when it's high enough, then we have a very high probability of surviving. And if I increase the barrier, then I need to increase the density of the atoms more. That is, I need to increase the interaction strength more in order to survive superfluidity with a higher barrier that's constricting the flow more, that's making the velocity of the atoms higher. And we can plot that interaction strength versus the barrier height, where we stop the flow, getting a picture like this with no hole, compared to when we retain the flow at low barrier height and at at high interaction strength, we retain the flow, and at high barrier height and low interaction strength, we lose the flow. And if we plot the velocity relative to the velocity of sound against the density, which I've indicated here in terms of the speed of sound, because remember, the speed of sound depends on the square root of the density, then we find that it seems to be pretty constant, lower than the speed of sound. Why is it lower than the speed of sound? Because we can do more than create phonons. We can create vortices. And back in 1955, Richard Feynman came up with a theory for why this would happen, came up with an expression for what the velocity would be, excuse me, for what the velocity would be to break the superfluidity. And we plot our that predicted velocity here, and you see that it's in pretty good agreement. The fact of the matter is, we're not sure we understand why it's in such good agreement, because Feynman's treatment was extremely simplified and for a particular geometry that we don't have. And so all we can say about this is that it appears that phonons are not the thing that's creating this dissipation, that instead we believe that it's vortices, because those are the other elementary excitations. But as far as the details, we're still trying to understand that. Now we've done some more experiments in which we actually move the barrier. Why do we move the barrier? Because if we were to go into the rotating frame, rotating with the barrier, then we would see that there is a fictitious force, a Coriolis force, that looks just like a magnetic field if these were charged particles. So that means we're doing something that's analogous to putting a magnetic field onto a ring of superconductor. So that sounds like an interesting thing to do. And just to give you some idea of the kinds of parameters that we're looking at, we're talking about circumstances under which the speed of sound would circulate around here at a rotational frequency of 35 hertz, that if I have 1 unit of angular momentum, then the atoms are circulating around here at a little bit less than 1 hertz. The size of these rings, in case I didn't mention it before, is about a mean radius of about 50 microns. And now we're going to move this this barrier around here to see what happens. And we can move it at various velocities. And depending on how fast we move it, we get more or less angular momentum spun into our system. If the velocity is low, then we don't get any angular momentum at all. If the velocity is moderate, then we get a small hole indicating only 1 unit of angular momentum. And if the velocity of rotation is large, we get more units of angular momentum. And the point is, here, this was just to show that the angular momentum is quantized. We don't get just any unit of angular momentum. The size of these holes, which is some measure, which is a rather complicated measure of how much angular momentum there is, but it's quantized. We don't get values in between. So this tells us something that we always knew, that the angular momentum is going to be quantized. And this shows how this goes as a function of how fast we rotate. That if we rotate very slowly, we don't get any angular momentum in. If we rotate fast enough, we get 1 unit of angular momentum, and for faster, then it doesn't produce any more angular momentum until we reach a second critical velocity, and then we get 2 units of angular momentum in there. So if we change the chemical potential, that is the interaction between the atoms, that changes the velocity that we have to rotate in order to get angular momentum to come in. Okay, so all these things are behaving just the way we expect them. Now I want to, well, gee, there's so many things to tell you about and so little time. And I think that I've probably included too much in this talk, but there is hysteresis. So what is hysteresis? Well, if I have a ring where the atoms are not moving, and I increase the rotation of the barrier, there will come a critical velocity, as we've seen, where I will induce rotation, and afterwards, this tells me what the probability of there being circulation, and once I reach that critical value, then I've got a high probability of getting rotation. Now, if I increase the height of the barrier, I don't have to move it as fast in order to induce rotation. That's not surprising, because this barrier constricts the flow. The more I constrict the flow, then the higher the velocity is past the barrier, and the more likely it is that I'm going to induce a circulation, because it's when that velocity exceeds some critical velocity that I'm going to get circulation. So this set of pictures is just what you expect. I can go the other way. I could start with circulation in the ring and then reduce the velocity of the barrier. So let's say I start with the velocity of the barrier moving with the atoms as they're circulating in the ring. So the fact that they're moving with the atoms means that they're not really perturbing the atoms very much. But as I reduce the velocity of the barrier, then the relative velocity between the barrier and the atoms becomes larger and larger, and eventually it'll cause the circulation to stop. And again, how much relative velocity between the atoms, which are moving at some velocity because they're in this state of circulation, the relative velocity between that and the barrier, which is being moved as well, that velocity has to be smaller in order to break the circulation if the barrier height is bigger. It's just the opposite of what happens when I'm spinning the atoms up. And so when I plot the two of these things together, there's a hysteresis curve. If I start with a non-circulating condensate, I go faster and faster and faster, and then I get some circulation. And then when I reduce the velocity, I make the circulation, I make the rotation of the barrier slower and slower and slower. And finally, the relative velocity of the atoms and the barrier is big enough that it breaks the flow. And I've got this hysteresis loop. So that's what I mean by hysteresis. And here it is. It's just what you expect. And it's an interesting thing because hysteresis behavior is something important in a lot of electronic circuits. So maybe it's going to be important for these fluid circuits as well. So we're almost done. I want to tell you about one more thing that's just really cool. What I'm going to do now is to make a trap that's in the shape of a target. I've got a central region where I am not going to spin up the atoms, and I got an outside ring where I am going to spin up the atoms. And what I'm going to do is I'm going to release the trap so that these two pieces merge together, and the inner piece, which is not rotating, interferes with the outer piece, which can be rotating. Now, first, let me show you what happens when nothing is rotating. The inner piece expands and overlaps with the outer piece, and it forms interference fringes. This is the actual picture, and here is a numerical simplification of where the rings are. So what you can see is I've got essentially circular rings. What that means is there's no gradient of the phase going around here because the atoms aren't rotating. I just get a phase that has to do with the motion of the atoms. When they're released, they move out, and that motion means that they have phase. They have a gradient of phase, and when the two pieces interfere, it produces these interference fringes. But whoops, I went the wrong way. Okay, so the fact that they're circular means that I don't have a variation of the phase around here. That kind of variation is what you get when you have circulation. And when I get circulation, now you see these fringes are no longer circular. They have this spiral feature. And depending on how much circulation, I get tighter and tighter spirals and more spiral arms. Here's 12 units of circulation. And if you count them, which isn't easy to do, you'll count up 12 spirals. Well, I think that we are through with the time that I should have spent. So I'm going to just eliminate this one that has to do with the dragging of a standing wave of sound due to circulation, and just show you a picture of a number of the teams that have worked on this over the years. I want to particularly mention Gretchen Campbell, of course, who's been the leader of all of this. Chris Laub, by the way, is an expert in superconducting circuits. So he was very important to us in trying to understand these rings in analogy to superconductors. Steve Eckel was one of the major movers of this as well. And students like Monica and Avinash and Swarnav have been very important in making all of this, and Neil in making all of this work under the leadership of Gretchen Campbell. So there's lots of open questions. There's lots of experiments going on with superfluid rings, and they're a long way from making applications like rotation sensors in the way that conducting circuits are sensors of magnetic fields. But that's all that I have time to tell you about now, and I'm very eager to get your questions. Thank you very much. So, Vanderlei, are you there? And do we have some questions?
Oh yeah, I'm here. Okay, we have a lot of questions. Let's
Beautiful.
First, we're going to start with the question for the people here in the auditorium. So Holly, come up. We have a lot of questions from people in the YouTube. So be patient, and we're going to try to answer all.
Hi, it's just a small curiosity. If you had one ring that had a circulation and you had another ring next to it, is it possible to see a jump from one ring to the other?
Yeah, so that's a very good question. So first of all, let me. So I'm using this to sort of illustrate. Are you imagining like another ring out here, or another ring sort of on top of it? Actually, the answer is very similar. We can imagine doing both things. We haven't done it, but we can imagine doing both things. Well, okay, so here's what we think would happen. We don't know because we haven't done the experiment yet, but we have been thinking about it.
Okay.
If the separation between the rings is such that the one ring can communicate with the other one, in other words, there's going to be a barrier between the two rings. We're going to form some sort of potential that's going to create these two rings. If there's no ability of the atoms to go from one ring to the other, either by tunneling or just by leaking over the top of the barrier, then these two rings are going to be completely independent of each other. But if we release the atoms, then we'll see interference between the rings. And in fact, we've done some simulations about what would happen with the interference, depending upon whether, let's say we had an inner ring and an outer ring, depending upon whether the inner ring or the outer ring was the one that was rotating, the direction of these spirals will reverse, even though the rotation is always in the same direction. So that's something interesting that would happen, but it really doesn't get at your question, which is what would happen if I have some coupling. I think that's the really interesting part of your question, is what if I had some coupling? And well, we can do some simulations, but what would actually happen, we have to do the experiment. In a very ideal case where I have a coherent coupling between the two rings, what I would expect to happen is that the circulation would be transferred from the one ring to the other. And just how this would happen, whether this would be as a macroscopically coherent phenomenon, I just don't know. It's one of those things that we really would like to understand better, but we don't. What a great question.
Okay, thank you, Bill. Now we have another question for another participant.
Hello, Bill. My name is Luis, and I have a question that is sort of an intuition question. So the way you set up the experiment and showed me some of the ramifications, it reminded me a lot of quantum Hall effect and quantum spin Hall. Mainly when you put the steering, it might be the magnetic field and separation of the speeds and such. Is this intuition correct, or it's not a good analogy?
Yeah, no, it is a good analogy. It's just that you very correctly identified that what we want to do to see quantum Hall effect or spin Hall effect is we need to have something that's the analog of a magnetic field. That's exactly right. It turns out that this isn't the most convenient way, that is rotation, isn't the most convenient way of getting that analog magnetic field. And there's another way. So one of the members of our group, Ian Spielman, invented a way of producing a synthetic magnetic field that's different from rotation and has all sorts of wonderful advantages. And boy, I wish I had time to talk about that, but that's a whole other lecture. But if you look up Ian Spielman and synthetic magnetic fields, you'll find a number of papers that he's written, basically by using a combination of a gradient of the magnetic field so that you change the resonant frequency of the atoms in space, and counterpropagating laser beams that he can create a vector potential, an analog to a vector potential that has a curl and therefore has a magnetic field. And he has done just what you're imagining. He has seen a Hall effect and a spin Hall effect, not yet a quantum Hall effect or a fractional quantum Hall effect, which we really want to do, but we're going in that direction. So yes, but slightly differently.
Okay, one more question here from the audience.
So first, thanks for the wonderful talk. I was wondering, when you show those probability of observing or not the flowing after triggering a barrier, those probabilities are related to quantum fluctuation in the angular momentum as a observable, or in the number, or in the observable to measure the number of particles still flowing.
Yeah. Okay. So here's an example. I should have shown you the raw data. If I showed you the raw data, then it would either be flowing or not flowing. But I think you understand that. Your question, that is, what are the fluctuations due to? And the answer is, we don't really know yet. It's one of the things that we're still studying. So we believe that the fluctuations are at least in part due to thermal fluctuations. And one of the reasons for this is that as we change the temperature of the atoms, we can see the way in which this these curves goes will change with the temperature of the atom. So we do believe that thermal fluctuations have something to do with it. We also believe that it may be something that's totally trivial. That is, it may be that there are mechanical fluctuations as well. Our apparatus is not completely stable. We try to stabilize everything as best we can, but anybody who's made one of these apparatuses know that they vibrate a little bit. So there may be some mechanical vibrations. We would love it if it was due to quantum fluctuations, but at the moment, we're not really sure that anything that we're seeing is due to quantum fluctuations, but that's what we want, is to be in the regime of quantum fluctuations driving these transitions.
Okay.
But we don't know yet.
Thank you, Bill. The promise, we have many questions here in the audience. One more, and then we go to the YouTube, otherwise.
Hello, Bill. I'm Pedro. Pedro, yeah, my name. So, what would you observe if you used other shapes in the laser instead of rings, using ellipses?
Yeah. So we haven't done that. Well, we've done some things where we've put two barriers and moved them relative to each other, which is a little bit different from what I've shown you here. But the reason we wanted to use rings was because we wanted something that was cylindrically symmetric. If the potential is not cylindrically symmetric, as you're suggesting, and of course, why not? Then it's not going to be a potential that conserves angular momentum. So that means angular momentum will no longer be a good quantum number. Now, I think that's a really interesting thing to study, is a situation where angular momentum is not a good quantum number. Because, in most of the things that we do, we assume that angular momentum is a good quantum number. Now, what would be the case when angular momentum is not a good quantum number? Well, one of the things is, well, what is a good quantum number? And I think the thing that we should think of more carefully is that phase winding becomes the good quantum number. When you go around the ring, the phase of the wave function of the atoms has got to change by a multiple of 2 pi. If it doesn't, then the wave function is not single valued, and that's just not allowed by physics. So it always has to be 2 pi, or a multiple of 2 pi, whereas the angular momentum does not have to be the same as we go around. It doesn't have to be in an eigenstate of angular momentum. So what is the meaning of that? Okay, I'm not really sure. And I think that doing some experiments and thinking about experiments where we use different shapes might help us to think more clearly about what happens when angular momentum is not a good quantum number, but something like winding number is. I wish Gretchen were here because she's thought about this much more carefully than I have. This is really something that I think needs more study, is to understand what are the conserved quantities in these in these situations, and what is the significance of having different conserved quantities than the ones that we know and love. These have been great questions.
Thank you. Bill, there is one more question here, then we go to the YouTube. So.
Yeah.
Hello, Bill. My name is Bruno. First of all, thanks for the great presentation. It's always a pleasure to learn with your presentations. So I think my question is a simple one. It's an experimental point of view. And I would like to know how you produce the ring shape potential. I think it's with a laser blue detuned laser, and you produce a red detuned laser through the trapping behavior. So I don't know if it is way, but I think it's a simple question.
Right. So let's go to the picture that I had of the all optical trap. Okay. So I think you understand how we make this part. We just start with an ordinary Gaussian laser beam. We put it through a cylindrical lens. I mean, there may be a little bit more complicated optics, but we just make a sheet of light, and we make this the parameters such that the waist of the focus is long enough that it's longer than the size of the ring, which, as I mentioned, has an average diameter of about 50 microns. So that's pretty easy to do. Now, this one is the one that's really interesting. How do we make the ring? And the answer is we use a diffraction grating that, boy, I wish I had a picture of it. I didn't include a picture of the diffraction grating. We use a diffraction grating that, okay, so first of all, imagine a diffraction grating that just has straight lines in it. And now what I'm going to do is I'm going to make a diffraction grating that has a fork in it. That is, I'm going to have one fewer lines on one side than I have on the other. And somewhere in here, see, this line's going to connect to that one, and this one's going to connect to that one. And these two are going to connect to this one. That's what I mean by a fork. So if I have a diffraction grating like that, and I shine a Gaussian laser beam onto it, then the first order diffraction pattern is a ring. It's a Laguerre-Gauss beam. So if I start with a Gauss beam, the first order diffraction is a Laguerre-Gauss beam with 1 unit of circulation. So if I were to, in fact, I think that the thing that I didn't show you actually, okay, so this is what a surface of constant phase for the light looks like for a Laguerre-Gauss beam that has 1 unit of circulation. It looks like this corkscrew, and I think I can, now if I let the thing propagate, it looks like that. So that's what the light looks like that has this ring shape, and that will allow you to create this ring that is where we store the atoms. Now, the reason I had that, which I decided not to show because I could see it was going too long, is we can use that angular momentum of the light to spin up the atoms. And we used to do that, and it was beautiful, but it didn't work as well as stirring. Stirring is so easy. It's not very elegant, but anyway, the way we make these rings is by making these Laguerre-Gauss beams. And one of the ways of making the Laguerre-Gauss beams is to use a diffraction grating that has this fork-like structure, and the diffracted laser beam has the Laguerre-Gauss shape and therefore makes this ring. So I hope that answers the question.
Okay, thank you.
Great questions.
Bill, before I go to the YouTube questions, I have one personal question. I see some details on your necktie. Can you show to us, because that seems to be an official necktie of the Atomic Club.
Exactly, and you have one too.
Yeah. Okay, well, that's nice. And,
so
thank you.
Yes,
I was wondering if you're using the
physicists,
official necktie. I should be using too.
Well, I think that when atomic physicists wear neckties, which I think is only to give talks, then we should wear that tie.
Yeah, I'm going to come with my necktie tomorrow. I have here many questions from the YouTube. I'm going to try to go fast, so see if you understand. The first question is from Emmanuel. He says, thank you for the talk. In the phase sleep in the ring with a weak link experiment, can one go up and get an arbitrary large quantum of rotation in the system, or is there a fundamental limit?
Okay, so the answer is yes and no. There's not what I would call a fundamental limit, but there is a practical limit. So I'm trying to see if I can find a picture that will show what I want to illustrate. Well, anyway, okay, let's just look here. Here's the problem. We're rotating this barrier around, and that means that the velocity at which the barrier is rotating is higher on the outside than it is on the inside, because the barrier is rotating like a rigid body, okay? Because that's really the only way we know how to do it. Now, the velocity of the atoms is lower as you go toward the outside than it is on the inside, because that's the way vortices work in order to get angular momentum to be a good quantum number. So the barrier is moving faster on the outside, and the atoms are moving slower on the outside. So the relative velocity between the atoms and the barrier is not the same across the annulus of the barrier. So what this means is, when that difference between the let's say I go into the moving frame of the barrier, then the relative velocity of the atoms here and here are different. And when that difference is big enough that it can create a vortex, then I start to get vortices inside the ring itself, as well as circulation around the outside. So that's a problem, and it makes a mess. So how do you solve that? Well, you solve it by making this annulus narrower. But we can't make it ultra narrow because it's made with light. And light has a diffraction limit. So there's a limit to how narrow I can make this barrier. So that's one thing. Another thing is that, remember I told you that if I go into the rotating frame, that I will then have a Coriolis force, and the Coriolis force looks like a magnetic field, has the same form as a charged particle moving in a magnetic field, like the Lorentz force. That's all true. But in the rotating frame, there's another force, and that's the centrifugal force. So if I rotate too fast, then I've got a problem with the centrifugal force, and I can destabilize the trap. So these are what I would call practical problems, but it means that we can't rotate as fast as we want.
Okay, Bill, thank you. The other question comes from Abel Beregi, and the question is, on phase sleep slide, the 0 to 1 transition seems to be well resolved with nearly constant circulation after the transition. Why is the 1-2 transition not so well resolved?
Yeah, right. And the answer to that, I think, because it's not like we've studied this really carefully, but I think that the answer to this is mainly the point that I was making before, that when the velocity is higher, then we start to nucleate vortices in the ring. And this experiment was one of the early experiments where the ring was kind of fat. And since then, we've made the ring a little bit narrower, and I'm sure we have or could make better data than this, but what I'm showing you is sort of the first time we did it because, I don't know, maybe nostalgia. So I think the problem here was the ring was too fat, and as a result, we were creating extra vortices, and that, of course, changed things because sometimes we would have a vortex in the ring, in the annulus of the ring, and sometimes not, and it was not always easy to tell whether that vortex was coming from circulation or whether the vortex was coming from having an extra circulation in the annulus of the ring. So I think that's the main reason, but there may be other reasons as well. We simply haven't studied it carefully enough yet.
Okay, thank you. There is one more question from Pedro Magnani. Thanks for the great talk, Professor Phillips. Can you please explain more about ring stability? How do you keep the flow from heating up the condensate?
Yeah. Well, here it really is what you might call a classic case of superfluidity. If you okay, so I think we should go back to the question of why is something superfluid in the first place? Okay, there's what is this phenomenon of superfluidity? It has to do with whether or not you can lose the energy of flow to something else. And what is the something else? Well, there's only a few things that can happen in a superfluid. And that is, and the two things that we talk about here are phonons, that is quantized sound excitations, and vortices, which are quantized excitations of circulation. Those are that's the way we get rid of energy, is by creating those kind of excitations. That's the analog of friction. So if I've got an ordinary fluid like water moving through a pipe, then the energy of that motion is dissipated because there's friction between the walls of the pipe and the water. And in fact, if you keep pumping water through a pipe, you're going to heat up the pipe. Well, this is the analog of that. Creating phonons and creating vortices is the analog of losing energy to heat with a classical fluid. Now, the magic, so to speak, of superfluidity is that the nature of the excitations is such that you cannot create the excitations and still and still have a conservation of energy and momentum, which you must have in any kind of a process. You've got to conserve both energy and momentum. And how are you going to do that? Well, it turns out that for what we call the dispersion curve, the energy of a phonon relative to the momentum of that phonon, it simply cannot happen when the velocity of the flow is less than the velocity of sound, and that's why we have superfluidity. Now, things are more complicated when we have vortices. And so let me see if I can get Feynman's picture. Maybe not. Oh, I mean, it's in here someplace. So Feynman was figuring out this same feature. Yeah, so here he was imagining flow through a channel, opening up into an infinitely large reservoir. That's not what we have, but that's the simple thing that Feynman described. And what he figured out was that you could conserve energy and momentum by creating a string of vortices with a certain spacing that would depend on how fast the velocity was. And the critical velocity would depend also on this spacing here. So we plugged those numbers in for what our channel was, and we got something that looked like it agreed, but we don't really understand why. But the point is that this is a much more complicated situation. And the velocity depends in a complicated way on this dimension. So in our case, if we don't have a barrier, then we are apparently below the critical velocity for whatever is happening, and the atoms just stay forever. It's a lot easier to understand when you're talking about phonons. It's much more complicated when you're talking about vortices, but that's all there is. So if we can't make vortices and if we can't make phonons, then the flow is going to last forever. Now, when I say forever, remember, the vacuum is not perfect. And what happens is that if we wait a really long time, like a minute, then the number of atoms is going away. And the number of atoms going away means the interaction between the atoms go away. And that makes this number become bigger, okay? And that makes the velocity become smaller. And then things dissipate. That is, we finally get dissipation because the speed of sound becomes lower and lower, and eventually the speed of circulation in the ring reaches the speed of sound, or reaches something close to the speed of sound, when the density becomes small enough because the vacuum has kicked out our atoms. So that was a very long answer, but I hope it gives you something of an idea for why we have superfluidity and how we lose superfluidity.
Okay. That is, well, we have, I'm going to select one or two more questions.
Before you go to the next question, you're an expert in superfluidity. Would you like to add anything to my explanation about superfluidity and why things don't dissipate? Because you're a real expert in this.
Well, thank you for the compliment, but I will put another questions and we can complement at the end. Sergio Muniz send you nice regards. Thank you for giving the talk. And he asked a question. And the question, well, the problem is many questions are arriving and my screen cannot afford all. Okay, the question is, the width of the interference ring spirals depends on the radial velocity of the central back. Is that true?
Yeah, let me, now, again, this is one where I wish that Gretchen were here.
Yeah, well, I mean, you don't need to answer right away, we can.
Yeah, so if I understand the question correctly is, what determines the distance between these interference fringes? Is that the question, do you think?
Yep.
Okay. So one way of thinking about this is as a kind of a generalization of a two-slit interference pattern. And the two slits are some portion of this ring and some portion of this central part. So the thing that's going to set this is how far apart these things are. And so that sort of sets the analog of the angle at which the interference pattern emerges from the double slit experiment. How far the fringes are, of course, also depends on how far away the screen is where you make the two-slit interference pattern if this were light. So if I wait a longer time, then these things are going to be further apart. So there are two things that determine what the the size of this interference pattern is. One is the initial geometry, that is, the diameter of this ring compared to the diameter of this this central spot, and the other thing is, how long do I wait before I take the picture? So I hope I said.
Yeah, no,
I hope I gave you the right thing. I haven't thought about this for a while. I think
but
that's the right answer.
you have two clouds in expansion, the center one and the ring one. So you have to take both into account.
Exactly. Exactly.
You know, I don't know if we can call this the quantum Newton rings, because maybe will be like equivalent. You have a central guy.
It's a little bit like Newton's rings, but you remember Newton's rings have this feature of the fringes getting closer and closer together. And you'll see that here, the fringes are pretty evenly spaced, like in a two-slit interference pattern, instead of like in a Newton's ring.
Well, that's why it's quantum. Okay, well, Sergio has another question, but I'm going to give a chance to Dalila. Dalila asks you a very nice question. Can you elaborate a bit more about that part of your talk when you mentioned that a well-defined quantum phase does not necessarily means coherence?
Okay. So I think maybe I misspoke. A well-defined quantum phase does mean coherence. It doesn't necessarily mean superfluidity. So let me just say a few more words about that. Let's imagine that I made a Bose condensate without any interactions. Now, we never do that because our atoms always interact, but we can imagine such a thing, and we can in fact even do such a thing by first making a Bose condensate using the interactions, and then turning the interactions to zero using a Feshbach resonance. So at least there's nothing unphysical about having a Bose condensate that does not have interactions. And in fact, that was exactly the kind of situation that Einstein was imagining when he first came up with the idea of Bose-Einstein condensation. And by the way, it was exactly the kind of thing you were thinking, Vanderlei, when you studied the nature of Bose condensation in a trap back when you were at MIT. You were thinking about a non-interacting Bose condensate. Now, that non-interacting Bose condensate, which is a completely physical thing, has the coherence that we associate with a Bose condensate. I mean, what do we mean by coherence? Well, the coherence, one way of thinking about the coherence is it means macroscopic occupation of a single quantum state. That gives you both first order and second order coherence. And the Bose condensate has that, whether it has interactions or not. But if it has no interactions, you will not have superfluidity. The nature of the dispersion curve, which I alluded to before, which for an interacting Bose condensate has a linear dependence of energy on momentum until you get to the speed of sound, and then it becomes quadratic. Instead, with a non-interacting condensate, is quadratic from the beginning. That is, it looks like a free particle. And that free particle dispersion curve does not have the protection that the phonon dispersion curve has. And so the non-interacting Bose condensate is not superfluid, but it is coherent. So that's one example of how the two can be different.
Thank you, Bill. You know, you may have coherence, but not superfluid. That was the phrase that Bill said.
But if it's a Bose condensate, it will be coherent.
Yeah. Thank you, Bill. There is one more question. I'm going to apologize to Sergio Muniz about his second question, but there is one question from Bruno Vasco. Hello, Bill. Could you talk a little bit more about why it is so hard to measure the rotation in the technique without the spirals?
Yeah, well, it turns out it's easier to measure the rotation in the spiral one than in any of the other cases. But let me see if I can show another picture here. okay, when you look at that picture, if you just look at this one, it's just, because it's kind of noisy, it's just hard for me to look at this and count how many spirals there are. That's why we developed an algorithm for drawing these spirals on here so that we could count them up. So when I said it's not so easy, what I meant was just looking at this picture, it's hard for me to just look at this picture or these pictures and say, yeah, that's 12, right? But if you're careful and look at these computer-generated spiral arms, then you can do it. It's a lot easier, for example, than, let's see if I can show this. Yeah, looking at the size of these holes and trying to determine how much angular momentum is there, that's very difficult, okay? And we really can't do a good job once this number gets bigger than, I don't know, 4 or 5, whereas we can go up, you saw 12, and it's quite unambiguous. Whereas here, so this is the one that's really hard to do. So I was not being very careful when I said it was hard to do. It's only hard to do if you don't look carefully.
Okay, so we have a few more questions, but I apologize. We're gonna have to quit because we have a talk by Dan Kleppner that you know very well in 1.5 hours. And Dan Kleppner is going to speak to us about the deep history of atomic and molecular and optical physics. So I want to invite you also to join the YouTube and see the talk of Dan Kleppner if you can. We will be in 1.5 hours from now. But now we're going to have
we get to watch those later too, because they're going to be recorded and posted, right?
Yeah, you can see later, yes.
Yeah, because unfortunately I have to be someplace else and I won't get to see Dan's talk, but it sounds wonderful.
Yeah. Okay, Bill, I want to thank you very much for your kindness to be with us and give us so nice talk. I know that if we keep putting questions, you're going to keep answering until the end of the day. So I thank you very much for this big
and Sergio, send me your question in an email, because I know it's going to be a good question, because I know you.
Okay, so we're going to collect the rest of the question and send it to you. And thank you very much once more, and let's give a thank you to Bill.
It's a real pleasure. Thank you.
Okay, Bill. Bye-bye.
Bye-bye.